Yo, what's up? I'm James, and today I'm going to show you guys how to solve this medium difficulty leak code problem called maximum value at a given index in a bounded array. So this problem was pretty tricky for me to get the optimal solution, but today I'm just going to walk you guys through how you can go from the intuitive approach to the most optimal. So in this problem, we are given three positive integers, n, index, and max sum, and we have to create an array that satisfies these conditions. So the length of the array has to be equal to n. Every element in the array needs to be a positive integer, so greater than or equal to 1, because that would be, we can't include 0 or negatives. The next condition is that each, essentially what this is saying is for every element, the difference between that element and its neighboring element has to be less than or equal to 1. Okay, so that really means that between every element in an array, the difference can be 1 or 0. So it can be an element's neighbor can be that same element or differ by 1. Then we got the sum of all elements of the array does not exceed max sum. Okay, that's one of our inputs. And then the element at index, which is one of our inputs, is maximized. So then we return that maximized element, not actually the array we're constructing, just the element. And yeah, so in this example 1, we see we have these inputs and we output 2, right? Because 2 is the maximum value that we can place at index in this case, right? So in this case, index is 2. We have to do 4, the array has to be 4 elements long, and the sum of all the elements can't go above 6. Okay, so we have 1, 2, 2, 1. And if you notice, like, there's another array that satisfies this, be 1, 1, 2, 1, but that doesn't matter because the element at our index is still 2 in both valid arrays. Okay, so this is pretty interesting, right? So if we think about how to solve this intuitively, like the most straightforward way we can think would probably be figuring out what our bounds are for this element at index, and then we could just test every element in that bound or in that range and see if we can create a valid array around it. So if we think about our base cases, so an array of length 1, and we're given a maximum of, let's say, 6, and we're supposed to maximize index 0 because that's the only index, then the value would be max sum, right? So that's as high as num's index can go, is max sum. And as low as it can go, well, I think given the opposite case where we have a long array and the max sum is literally the length of the array, right? Every element's 1, so all adds up to max sum. So that the least it could be is 1. We also know that from this constraint that has to be positive integer. Okay, so what we can do is check every value between 1 and max sum at index and see if that's valid. Okay, so let's make that first brute force approach, right? So let's do a loop, standard for loop here, where I is less than max sum and we increment I. Okay, so I'm gonna say I is less than max sum here because whoops. I'm saying I, what the fuck? Oh, So I'm saying I is less than max sum here because once we hit max sum, once I reaches the maximum value, we know that that is the answer, and we're gonna return inside this for loop. So you'll see here. So we created our array nums. Let's just initialize it. We know it's n, and we know that everything has to be at least 1. Okay, and then we know at index we're going to set that to I, right? We're testing every value of I, and actually this starts at 1. And then, so let's build the left side of the array. So fill out all the values. So let's just say, let's make a new loop. And let's go from the left. So that's going to be index -1. And j has to be greater than or equal to 0. And j minus minus. We're decreasing. All right, so here we say nums of j is equal to the right element. The element to the right would be +1, -1, right? So the reason we can say this is because if we think we're trying to maximize the value at the index and minimize the total sum. So the way we can do that while staying within these constraints is from our index, every element to the right and left needs to decrease. Everything needs to go down, right? It wouldn't be like, it'd be allowed for us to put the same number to the right and left. That doesn't break the rules, but it's not going to maximize, or it's not going to minimize our max sum, right? We want to maximize one index while staying within our max. So the way we do that is just ensuring that everything to right and left is decreasing. And once we've decreased from our max from our mid or peak, which is the element at num's index, once we get to 1, we can't decrease any further, right? So we have to do max of 1 or the last element -1. Okay. So that's for the left side, and then for the right side, we'll just flip it. Okay, so now that's the right side. Okay, so we built the array. Now we need the sum. So let's create another variable, and we'll do a JavaScript reduce to add up all the elements by just saying as we accumulate, add the number. All right, so we have our sum, and now what we have to say is if our sum goes over max sum, let's just return let's return the last value that passed, right? So we'll start at 1. If this passes, if we're less than max sum, we'll try a bigger number. If we're less, try a bigger number, and keep going until we go over. Now we know it was the last number that didn't go over. And then, so let's test this. See if this works. So we passed these 2 cases, great. Let's try submitting this. And yeah, there we go. Okay, so we get the wrong answer here, where we have an element, or we have an array of length 1 at index 0, max sum. Okay, so this was one of the base cases I mentioned, actually. So we're returning undefined because we're going through this whole loop. I is becoming max sum, and then we never return anything. So what we can do here, we could actually say, instead of calling this I, we could call it like max value, right? The maximum value at this index. We know it's at least 1, so we can just say max val here, and we'll just replace all instances. That is actually it. Okay. and that. Okay, so then once we go through the whole loop, we know we can return max value because we know that that's as high as we can go, and every value before that was passing. So we'll submit this. Yeah, we have to say max val here and max val. Okay, so now we're passing a few more test cases, but we're failing this one where our max sum is a huge number, right? And that makes sense because we're going from 1 to max sum. We're looping, right? That's a huge compute, right? We're doing way too many operations because we're going up to a huge number. So instead of testing every value, what we can do is choose a random value. If our sum is too big, try a smaller value. If the sum is within range, we can try a bigger value until it gets too big. Okay. So that is a binary search, right? Because that's essentially what the essence of binary search is, right? If we binary search our element is too big, then we look for the left side, look for the smaller. If it's too small, we look on the right side, right? So essentially what we're doing is binary searching between 1 and our max sum, right? Here we just iterated through every value, but we can binary search to find the optimal value. So down here, I'm going to write a while loop because binary search needs a while loop. We need a left and we need the right. And the right is max sum. That's as high as we can go. While left is less than or equal to right. We find our midpoint, which is always we do math.floor to round down, and we say left plus right over 2. The thing about this is if these are two huge numbers, we could overflow. So what we can actually do is say like left minus or right minus left. Divide that by 2, add that to left. Now we know that right minus left will be a smaller number. So that's just good practice. If you're wondering why sometimes binary search uses left is less than or equal to right, or left is just less than right, it really just has to do with how we are handling our right bounds most of the time, right? So in this case, since right is max sum is a value that we could that could be our answer we're searching for. It's right is an inclusive bounds, so we use left is less than or equal to right. Additionally, so when we are updating our left or right, if in this case we're going to set right equal to mid minus 1. But if it was left is less than right, then we would just set it equal to mid, right? Because in this case, right would be like plus 1, and it would be an exclusive, right? A right goes one index past where we actually want to end our array at. So it just depends how we are approaching the binary search, right? Either one would work. All right, but essentially what we want this binary search to do is try a value. If let's create a function here, is valued, or we're calling a function that we haven't created yet on mid. So if we can use this midpoint at num's index and it's a valid array, then we can try a larger number than mid, right? So left would be equal to mid plus 1. Else, we set right equal to mid minus 1, right? So this mid was not valid. We do not need to include it. So we do -1. Okay, so we have that. Okay, so now we have to write our is valid, and that can do the same thing as what this is doing. We can construct an array. So let's update that. Is valid. Let's take in a let's just call it val, or we'll call it mid, and we'll construct an array. Same thing. Set this to mid. We don't need this anymore. And we'll construct our array on both sides, doing exactly the same thing we did before. In this case though, if sum is greater than, or first we'll say if it's valid, return true, else return false. Okay. So now instead of looping through every single possible value, we're using binary search to find the optimal. All right, so let's see how this runs. Okay, so there's just a typo. Okay, so we got more test cases, and here we're failing when our n value and our index value are huge. So, and our max sum is even bigger. Okay, so now we're getting time limit exceeded. Probably not because max sum, but because how big our array it has to be. Right, we're allocating huge storage space to a huge array, and then we're constructing. We're looping through every single element in the array, and this is just too slow. Okay, so this is a little bit faster, but it's still too slow to get the correct answer. So instead of constructing an entire array, we can mathematically figure out the sum of our entire array. Because we know the rules of how we construct our array, we know from our index we want to decrease by 1 on both sides until we hit 1, and then add 1s for the rest of the spaces, right? So those are like some pretty straightforward math for how we can get the sum. Okay, so let's delete this, and instead is valid is going to tell us the same thing but in a smarter way. Okay, so is valid is going to get the sum of everything to the left and then the sum of everything to the right, add that to the maximized value, and then tell us that way if our sum is correct. Okay, so now if what we have to find out essentially is the sum of a given sequence, right? We know the sequence is going to be mid 2 1. So add every element in the sequence of mid to 1 while we were decreasing by 1. All right, so this formula is called the arithmetic sum formula. Okay, and it looks like this. Okay, so the sum of a sequence with n terms is equal to n times the starting element, the last element, over 2. Okay, so if you think about this in the context of our problem, the starting element would be our mid point, the final element would be 1, and then the number of steps would be how many positions in our array we are looking for. And actually, the final term it might be 1, but we also might decrease to, we might not have enough positions to the left to even hit 1. Let me draw this out. All right, yeah, we have an array, and let's say blank, blank, 0, 1, 2, at index 3, 0, 1, 2, 3, we have 7, and then we have a bunch of indexes this way too, okay? So we want the sum of this, we want the sum of this, and let's say actually that this keeps trailing off, okay? This is super far to the right. So here we want the sum of 6, 5, 4, and we can't go any lower, right? So in our arithmetic sum formula, it'd be S equals 1, 2, 3, 3 sequence, 3 terms, and then we have our starting term, which would be 6 because we're starting from here. Ending term would be 4 over 2, right? So 6 4 is 10 over 2 5, 3 times 5 15. Okay, is that correct? 4 plus 5 is 9 plus 6 15. Okay, cool. So you see, we can use this formula to get this, and then in the other case, right, where there's a bunch of positions trailing off, and we'll go from 7 all the way to 1 and then have a bunch of 1s. All we have to do there is get our sequence from 7 starting term to 1, and then add all the remaining positions, right? Which is, it's 1 in each position, so we just add how many remaining positions there are. Okay, so that is the logic for like how we're gonna mathematically figure out the sums. So what we do here is start with the variable left count. Let's call this left count. This is all the positions to the left of our midpoint, or our index, right? So that is literally index, right? That in a 0 indexed array, at index 5, there's 5 positions to the left. There's 0, 1, 2, 3, 4, right? So 5 positions to the left of our index point. The positions to the left is literally index. And then from to the right, similarly, would be index minus, or actually the length minus index, and then minus 1. Okay, because the length of our array minus the index we're at, so index from the left, it's going to give us the other part of the array, right, that we're missing. And we do minus 1 because we're talking about indices. So our length is going to be like 1 greater than what we actually want here. So that's for the amount of positions, and then we'll have another value, steps to 1, right? So this is how many positions we need to increment to 1, right? And we need to know this because that's when we stop our sum formula, and that's when we just add 1s. So that's going to equal steps to 1 is our value minus 1, because if I draw this out again, if we're starting from 7, then we want everything to the left, and then we'll add 7 separately. We don't want to include 7. We want to start from 6, actually. Okay, so, and how many steps to 1? 5, 4, 3, 2, 1. All right, 1, 2, 3, 4, 5, 6. Okay, 6 steps to 1 from 1 position to the left of 7, right? So 6 total positions to get to 1, right? We need to know this because that's when we stop our arithmetic sum formula. Now we can say, well, if there's more positions, then or if there's less positions than we need to get to 1, then we don't have to add any ones. Our arithmetic sum formula is going to stop short of 1. Okay, so we can say we'll have a sum set equal to mid, right? Because we could just set to 0 and add mid, but we'll just set it to mid, and then we'll add our formula. So again, our formula is sum is equal to n times the first term plus the ending term over 2. Okay, so the number of steps we already said would be left count times, so our first term is steps to 1, right? Mid minus 1, first element to the left of mid, plus our final element, which would be steps to 1 minus left count plus 1. Okay, so yeah, the steps we need to get to 1 minus the actual positions we have available plus 1. So if we visualize this again, say from let's say it's 4, and let's say we're 4 at index 2. Okay, so steps to 1 is 3. Right, we need 3 steps from 4 to get to 1, but we only have 2 positions. So it's 3 minus our 2 positions. That would give us 1. But if we notice, we're only going to get to 2 on this final index. So it's plus 1. And that's just because if we were trying to figure out from 4 to 1, then we just do 4 minus our spaces, right? Our index, so 4 minus 2, and it would get 2. But since, we're counting from our next position over, we have to add 1 because we subtract 1 here, essentially. We just do over 2 because that is the formula. Okay, so that's when we don't have enough positions to get to 1, or just enough to get to 1. Otherwise, what we need to do is we know we're going to get to 1, so we can actually add, so the formula would be n, our first term, plus our last term is 1 over 2, okay? So in this case, we do steps to 1, right? Steps to 1 is less than our left count, right? So steps to 1 times our starting element, which is the same thing. It's the exact same thing, mid minus 1 plus 1 over 2, okay? That is the arithmetic sum formula starting from an element to 1 with n terms, right, in our sequence. So that's all the elements to 1, and then we have to add the following ones, right? So then we just add left count, since left count's greater, minus steps to 1. So that's how many trailing ones we'll have, right? It's just all the positions left over after we get to 1, right? Okay, so that is the left side of the array. And now we need to do the right side. It's basically the same thing. We're just going to switch around some values. So we have our right count. Steps to 1 is actually the same. And then we just swap in right count here. And that is all we have to do. We're just doing the exact same thing on the right side, and we just are, since we're still doing a decreasing sequence in both directions, the only thing we need to change is how many positions are on the right. And now all we have to do is add in this condition we had before. If sum is less than or equal to max sum, then return true, else return false. Okay, so let's run this. See what's up here. And I misnamed that. Okay, our base cases. And there we go. So this solution passes because it is optimal, right? With even huge numbers in our input, we aren't constructing or allocating any space to a huge array. And we don't have to do any loops here. We just do only math, and we can figure out the sum. So in our binary search, optimizes even more, right? Okay, so hopefully that made sense. Why we use this formula, how it can optimize our code, and how we can get there, how we can arrive to this solution from intuition, right? We take our intuitive approach and we optimize one step at a time, right? And we can get here. So yeah, that's it, guys. Thank you for watching. And if you have any questions, please leave them. Please ask away, whatever. Yes, thank you for watching, and I'll see you guys next time in the next problem. Bye.